Welcome, this is Dr. Plague, and today I'm going to present a few of my Plague tips on the designing and building of homemade CPUs. I have breadboarded up a lot of projects over my lifetime, and there are a few things I have learned to create a successful project. Now, some of these tips you may have already heard of, and if so, great. But if not, you may want to consider some of these ideas. And just as an FYI, you may not always see me following my own advice. Bad on me, but anyway, I'll just give you a few of my suggestions for a hopefully successful build. Be sure to stick around to the end as I'll talk about and demonstrate some of my upcoming video ideas. Specifically, I'll talk about what I plan on doing with the CPUs that I'll be designing and building. I'm sure some of you are wondering what these homemade CPUs will be used for, so stick around for some answers. Now, on to a few of my tips. When I'm designing CPU circuits or any circuits that use 74 series logic, I like to use something to reference the pinouts of the ICs I'll be using. Consider this collection of index cards. I've got an index card for each 74 series IC that I have, such as this 7404 hex inverter. If you look at the cards, you can see that I put the pinout on one side, and if we flip it over, I've added all the info I need to breadboard this IC up. Here's a quad 2-input NAND gate, and you can see there isn't any more info on the back, since it's pretty much self-explanatory. Here's a binary counter with some info. And here's an 8-bit magnitude comparator. I like to lay these cards out in front of me when wiring these ICs up. I'll grab the card for each IC I'm currently using and have them all visible. Really comes in handy. And in this kit, I have spare cards for new ICs, more dividers, and pens for drawing up new cards. Also, back here I have a bunch of 3D printed templates to help keep the drawings neat. I have templates for different sized ICs. I have them with the pins and without the pins. I'll first trace the outline without the pins, then I'll just add in the pins with the next template. You don't need to get this fancy, but you might want to think of some way to reference pinouts as you build your own circuits. And one thing I want to mention is that if you reference data sheets for your pinouts, you need to be careful and check the pinouts. Many data sheets do have typos in them. Let's look at this TTL book that I have. And we'll look at the 74LS123 right here. Take a close look at that pinout and compare it to this datasheet I got online. Many of the pins don't match up, and not only that, the typo on the left shows a 14-pin chip, while the one on the right is a 16-pin chip. The one with the typo on the left was revised in December of 1983, while the corrected version was revised in March of 1988. There's also an issue with the 74-122 and the packages, but this just gives you an idea of the type of errors you can come across. Now, let's talk about assembling the CPU circuits. There are a number of ways you could assemble your circuits. I'll most likely be using solderless breadboards for my builds, but I do plan on transferring them to PCBs in the future. These breadboards come with bus strips attached to them, but you can buy just the bus strips like this. So, you can build yourself buses and runways and such. At some point, you may want to consider transferring your builds to some type of PCB for a more permanent solution, such as these here, which I purchased from Micro Center. And I'm lucky enough to have a local brick-and-mortar Micro Center in Minnesota where I live. You could also design your own PCBs. There is a learning curve to it, but it's not that difficult. With these here, you get 5 boards for only $4.99. That's $1 a piece, which isn't bad at all. These actually look like some pretty decent plated through-hole boards, and I'm pleasantly surprised with them since this same SKU used to come with 5 much cheaper single-sided PCBs like these. I noticed a review on Micro Center's website that stated that these are now plated through-hole. So I had to go see for myself. And to my surprise, that person was correct. Now, I did build my programmer that I had a series of videos on those cheap PCBs. And now I wish I had waited for the plated through-holes. Then I wouldn't have needed to glue some parts on it. You could also buy other plated through-hole boards, such as this one, which was over $13 a piece at DigiKey. So, I would recommend if you've got a Micro Center near you, then you might want to get some of their PCBs. Now, if you're going to build your project on a PCB, then I would recommend using some type of sockets like these. You can get them in all different sizes. They come in handy if you ever need to replace an IC on your board. That way you don't need to unsolder it. Just pull it out and replace it. You never know when you're going to destroy an IC with an electrostatic discharge. Because of that, you may want to look at adding some ESD protection to your circuits. But typically, you only add it to parts that interface with the outside world, such as I/O ports and the like. You also want to have some type of ESD protection in your work area, such as a protective ESD mat. I typically wear either a wrist strap or ankle strap when working with electronics. When you see me on camera, I'm usually using an ankle strap to keep the straps out of view of the camera. On my workbench, I use one of these workstation monitors. It lets me know if there are any faults in my ESD setup. It monitors my mat and straps. Let's say I take an ESD strap and plug it into the first port here. Then it will beep at me if I'm not in contact with the strap. All I need to do is grab the wrist strap and it stops yelling at me. And if I plug a second strap into the second port, it'll yell at me again until I grab the strap. Fantastic! Now back to breadboards. You really need to be careful when purchasing solderless breadboards. Not all breadboards are created equal. Don't try to go cheap on them, such as these here, $4.99 for one board or $9.99 for three. The 3-pack sounds like a bargain, but they do tend to disappoint. These are from Micro Center, and unfortunately I would not recommend them. It's a shame, because I like Micro Center, but I do not like these breadboards. They're kind of a hit or miss. These are what I'll use for building my larger CPUs. I bought these from DigiKey. They are global specialties, and although they're not the greatest, I have found them to be satisfactory for the price. Let's take a closer look at the cheap ones from Micro Center under a microscope. And let's take a look at some of these holes. This one looks very loose. And yeah, this wire is not staying in place very well. Look how that wiggles around. Very loose connection. Let's see what else we have. And look at this one here. It looks overly tight. I could be pushing all day and that won't go in. This one, that's not good either. If I push hard enough, maybe I can get this one in. And it's kind of stuck in there now. There we go. And look at that one there. Yeah, that feels pretty decent. And up here, these look okay, but they're not very well funneled. This board is just rubbish. Now let's look at a Global Specialties board. These look to be fairly good. Not the best, but acceptable. And this sticks in very nicely. It feels like it's making good contact. So don't go cheap when it comes to breadboards. You do tend to get what you pay for. Now, let's move on to how to supply power to our breadboards. There are some good ways to distribute power to breadboards, and there are some bad ways to do it. One of the better ways is to use a star connection, where each breadboard has its own power coming in directly from the power supply. Another decent way to supply power is to daisy chain it. Now, we need to be careful when daisy chaining, because there's a good way of doing it and a bad way of doing it. Let's say we want to supply power to all three of these breadboards. And let's bring power in up here. What we don't want to do is start connecting each of the rails up sequentially one after another, like this. While it may look like we're supplying power to each rail, let's test this out. I'll bring in this meter to measure the voltage. I'll start up here, and I'll turn on a 5-volt supply. Looking good so far. Let's test the next set of rails. Not too bad, and I'll just go down the line here. That's good. Also looks good. Starting to have some issues here, and definitely not good here. Let's wiggle these wires and see if we can make some better connections. Kind of flaky. Let's try this. Suppose we're drawing some current. I'll add in some 330 ohm resistors up here. Okay, let's put one here. And wow, look at that drop. I'll just take out the resistors. And notice how that goes back up. Way too much resistance with this type of connection. Now imagine that you've got all kinds of active ICs that are constantly switching. You'll have all kinds of noise on your power rails. If we're going to properly daisy chain this, we should bring a couple wires all the way down each breadboard and tap off of them. That way, we're daisy chaining through the wire and not through the breadboards. Let's use this red solderless connector as sort of a power bus and connect up the power through it. This will be kind of like a star connection, but through this solderless connector. I'll connect the incoming power into the center of it, and I'll just tap off of it to connect to each rail. Now I'm seeing 5 volts down there, and I'll start adding in some resistors. Not bad. Let's fill each rail with a resistor. And the last one took us down a bit. What if I had connected the power directly to that rail? Yeah, much better. So, the red connector was also a weak link. This just shows you how important power connections are. Make sure you're measuring the power on every rail when you build something up, and make adjustments until the power looks good. So now, with all those weak links that I demonstrated, we should talk about wires and power supply test leads. All wires and test leads will have some amount of resistance, and this resistance is capable of causing unwanted voltage drops. Let's measure the resistance of the test leads that I use on my power supply. And you can see that I'm getting somewhere around 76 or 77 milliohms. This may not seem like much, but let's send 1 amp of current through 2 of these test leads shorted together. And let's see. We get about 168 to 169 millivolts, which is about what I would expect given the resistance of the leads. If you have the proper test equipment, you may want to measure some of your wires, leads, or cables to see what you get. But before you do, make sure you have the correct type of meter and probes for making such small resistance measurements. You'll want a meter that supports 4 wire measurements, and a set of Kelvin probes such as these here. Each probe has 2 connectors and the internal wires join at the tip right here. This allows the meter to use 1 wire for sending current and 1 wire for sensing the voltage drop. These are single-pin Kelvin probes. You can also get Kelvin probes with individual clips. What you don't want to do is use a standard multimeter with single wire probes, because those wires to the probes also have resistance that will interfere with your measurements. Even if you null it out, it won't be very accurate at such low resistances. So, how can we ensure that the wire resistances don't cause much of a problem? For that, let's talk about capacitors. It's usually a good idea to add some bulk capacitance to your breadboards, along with bypass capacitors for the individual ICs. It's the bulk capacitors that'll help out with the wire resistances. Let's take this breadboard as an example. We have an IC placed on it, and we have power coming in here. And we want to add some bulk capacitance. 4.7 or maybe even 10 microfarads would be a good value for these. And we could add that just about anywhere. For example, we could place it up here, Or we could place it down here. Or another place we could consider is right here in the middle. And connect one side of it to ground and the other side to VCC. Now, of course, you want to use shorter wires than this. But that just gives you an example of how we could add some bulk capacitance to this breadboard. Now, when it comes to bypass capacitors for each individual IC, what I see a lot of people doing is they'll just take like a 0.1 mic cap and just throw it in right up here. The value is not too critical. You could use 0.1 microfarads or 1 microfarad caps or something close to that. Whatever you have. Something is better than nothing. But is this placement a good idea? Well, let's think about this. On a PCB, you'll usually have the luxury of a ground plane. But on a breadboard, it's not laid out quite so nice. The ground up here is not quite the same ground as down here. Even though they are connected over here, they are separated from each other. When there's a current spike drawn by the IC, it has to flow somewhere. Consider the IC as being a single node, and we know from Kirchhoff's current law that all current entering and exiting a single node must add up to 0. This means that any current coming into this IC must also exit this IC. Just like with the capacitor, same thing. If we're pulling current out of the capacitor, then the same amount of current must enter the other side of the capacitor. Now, in reality, some of this current could flow through other pins of this IC, but we'll just pretend we only have the power and ground pins to deal with. So if we have a current spike, we're going to pull current from the capacitor. It's going to go through the IC, and it needs to go all the way around here to get back to the capacitor. That's a large loop. And it could be inductive, which could create impedance at higher switching frequencies and limit the amount of current that the capacitor can supply. So, what could happen here is we could get some current going through the IC, and it could go through the supply or bulk capacitance and come back to the IC, thereby making the bypass capacitor less effective. We'll get kind of a superposition of the current going through the capacitor and current going through the supply or bulk capacitance if it exists. Now, obviously, this is better than nothing, and you could throw one in down here. That way, you would have one for sourcing current and one for sinking current. But this still isn't ideal. We still have a large loop. What you might consider is to add a capacitor directly from the power pin to the ground pin, like this. Notice how I placed the capacitor over the IC. Now, the leads on this capacitor are kind of long, but this loop is a heck of a lot shorter through here than to go all the way around here. It's kind of unsightly, and it kind of gets in the way of looking at your IC, so you might want to put it somewhere else, such as keeping this one up here. But if we keep this one, we might want to change the ground of the IC, such that it goes up to that ground rail. So we can connect it up to there, and of course use a shorter wire than this. But that just gives you the general idea. This way the capacitor is still across the power and ground pins of this IC. Another thing we could do is to put the power wires back the way they were, and place the capacitor right here next to the power pin of the IC. Now we could take a wire and connect the other side of the capacitor to the other ground. Or you could also connect it directly to the ground pin of the IC. Of course, use a shorter wire. I'm sure you could think of other ways to connect it up to give similar results, but these are just some ideas. Finally, let's talk a little about unused pins on our ICs. Whenever we connect up an IC, we should make sure that all the unused inputs have a defined state. We could either tie them or pull them high or low. But what we don't want to do is to leave them unconnected. Let me show you what can happen if we leave them unconnected. Let's take this 74HCT00 quad NAND IC as an example. I'll just place it on the breadboard here. Then I'll add power and ground. Now here's the pinout. And we can see that there are 4 2-input NAND gates, which gives us a total of 8 inputs. I'm going to leave them all unconnected and connect the power supply to the power rails. And let's connect a scope probe to the power rails to monitor what happens to it. Then I'll apply power and wow, look at how dirty that power looks. And it only gets up to about 4.5 volts. Also, we're pulling some nasty current too, up to about 10 milliamps. That did not look good at all. And that's due to some internal oscillations in the IC, which can be prevented if we provide a proper level to each unused input. So let's do that. I'll either tie the inputs to ground or VCC. I'll just connect the lower inputs here to ground and the upper ones to VCC. Now, we don't need to worry about unused outputs, just the unused inputs. We can leave the unused outputs unconnected. That won't hurt anything. Okay, let's power this version up. And look at that. We have 0 current draw, and the power rail looks very clean. And it's all the way up to 5 volts. Beautiful. So that wraps up my Plague tips for you. I may make more videos with additional tips in the future, but that's it for now. Now, let's talk a little about where I'll be going with upcoming videos. First of all, I'll be building the next homemade CPU, the Plague Mark II. This will be a very simple CPU, just like the Plague Mark I, but the Mark II will be much more programmable. It'll handle both input and output, be able to perform some simple calculations, and it'll make decisions with conditional jumps. Just like with the Plague Mark I, there will be at least 2 videos, likely several more devoted to the Plague Mark II. I'll also develop a simple assembler to use with the Mark II to help us with writing code. The Plague Mark III will be the first of a series of much more complex CPUs, which will have some serious computing power compared to the Mark I or Mark II. My current plan is for the Mark III to support over 200 assembly language instructions, and I'll talk more about that in a little bit. Before I get to building the Mark III, I'll make a series of videos on developing some video circuits. You may have noticed that I created some videos on the composite TV signal, and I'll be expanding on those. We'll start out creating some simple circuits to display black and white graphics on an old TV screen, or even a new one with the proper connections. I'll show how we can create some simple circuits to display simple text. Then we'll look at some different methods to generate color. And finally, we'll look into generating simple color graphics with different resolutions. So, my purpose of creating those composite TV signal videos was to prepare us for these future circuits so we can create some retro-style computer systems. So now, back to the Plague Mark III. What will it be able to do? Well, my plan is to develop a BASIC interpreter that can run on it. If you're not familiar with BASIC, it's a programming language that stands for Beginner's All Symbolic Instruction Code. It was used a lot in older computer systems, such as Commodores, Apples, and IBM PCs and PC Juniors. Unfortunately, I no longer have my old PET Commodore or Commodore 64. I wish I would have saved them so we could use those for demonstrations. But we can still look at the DOS-based GW BASIC for reference. The BASIC that I'll be creating for the Plague Mark III is called, appropriately, Plague BASIC, which I've already developed. And don't worry, I do plan on making videos showing and explaining all the code. I'll give a quick demonstration of it. This version has about 32K of free memory, but the Plague Mark III may not support that much. For some reason, people like to demonstrate code by printing "Hello World," so I'll do that. Then I'll just create an endless loop. Now, if we list the code, you can see that the statements are now in uppercase. That's because my version of BASIC tokenizes statements and functions and such. Now, if we run this, we can see that it does exactly what we would expect, and I can break out of it with Control-B. Unlike some lightweight BASICs that can only support maybe 26 variables, A through Z, my version will support any number of variables only limited by the available memory, and the names can be more than just one character in length. The user interface gives us a simple editor to enter in code. We can list it, run it, create a new program, we can also turn on trace mode and run it. You can see that it shows us which line numbers are being executed. And if we add some more line numbers in between lines, we can easily renumber them with the renumber command, which will account for gotos, go-subs, and such. My goal when making this version of BASIC was to make it fairly compatible with GW BASIC, so we can run almost any generic code. If you've ever read the book, The Scientist and Engineer's Guide to Digital Signal Processing, you may have noticed a lot of code written in BASIC. So hopefully we'll get some of that to run in Plague BASIC. And if you saw my tribute video on Tim Hartnell, I showed some books containing games written in BASIC. I would like to be able to run some of these in Plague BASIC. So let's take this maze program from this book, for example. It'll generate mazes along with their solutions, but I've only entered enough code to make the mazes without the solutions for now. We can enter the dimensions, and it gives us a randomly generated maze. And we can get through this pretty easily. And if we run it again, we get a different maze. We can make larger mazes and such. If I want to find out how much memory we have free, I can easily check that. And we can check how much memory was used during the last execution, which accounts for a variable memory space that was allocated along with stack usage. Now, in the tribute video, I demonstrated a golf game from this book. So let's try running it in Plague BASIC. And it runs just fine. I'll break out of this since Mrs. Plague isn't here right now. So this one didn't use much memory either. Just over 4K of bytes were used. But there was another game that I demonstrated from this book, Chateau Galliard, which used much more memory. Let's try running it in Plague BASIC. Now, to run this one, I need to run the command nocls first, because this program uses looped delays, which will run much too fast on a modern computer and will clear the screen before we can finish reading things. Instead of clearing the screen, the nocls command will cause it to just print a dashed line to indicate that there would have been a cleared screen there. And to undo the nocls command, we could just enter it again since it toggles on to off. And this one allows us to enter two-word commands. I'll tell it I want to go down. And it only accepts capital letters. So let's check the memory usage here. Wow, that used over 26K of memory. Not sure if I'll get that to run on the Plague Mark III, but we'll see. Now, this basic interpreter was developed in the language of C, but to get it to run on the Plague Mark III, I'll need to translate it to assembly language, since I don't yet have a C compiler for the Mark III, which I'll go through when we get to that point. Now, as an FYI, I did start converting it to Plague Mark III assembly language. I've also developed an emulator for the Plague Mark III, along with an emulator for a computer containing the Plague Mark III, all of which I plan to go through in future videos. Here's a quick demonstration of the Mark III version of Plague BASIC. I've only supported 8K here so far, but in the end, I'll bump it up as high as I can. And it operates the same as the version written in C. And you can see that it does support floating point numbers, along with trig functions and such. So, does this mean that the Mark III has floating point support? Actually, no. It can only do integer math, and it doesn't even have a multiply or divide instruction. So, how am I doing this? Well, it's fairly simple to develop floating point routines, and I'll go through that when the time comes. Also, I'll show how I'm able to support trig functions and other advanced math using what are called Cordic algorithms, which are coordinate rotation digital computers. These can be implemented in either code or hardware. Cordics are fairly simple to implement. If you want the sine or cosine of a particular angle, then you just rotate a unit vector for a certain number of times, each time by half the amount, until you get to the angle of the sine or cosine that you're looking for. Then, the x and y coordinates will be your cosine and sine values. At least that's a very simplified explanation. And we can do all kinds of math with these rotations and vectorings. I'll talk more about that in future videos for those that are interested. And be forewarned, it'll be a while before I get to that. Something else I plan on creating future videos on is developing a math coprocessor to use with the Plague Mark III. It'll be kind of like the 8087 math coprocessor, which was used with the 8088 and 8086. And look at this. If we search for the 8087 on Wikipedia, it says that it uses the Cordic algorithm. Fantastic! Interfacing the homemade math coprocessor to the Mark III will be similar to how the 8087 interfaces to an 8088. But unlike the 8087, my coprocessor won't support DMA transfers. The main processor will have complete control over the address and data buses, and the coprocessor will listen to them for escape codes, much like the 8087 does. And of course, the main processor will be able to continue executing code while the coprocessor crunches away at math calculations. We'll get into all that and much more. All kinds of fun to be had in the future. So, if you're ready for the ride, then stick with me. Well, that's it for this video. Thanks for watching, and I'll see you next time, right here on Dr. Plague.